coarsening via attention mechanisms, but I will somehow maybe come to that point a little later. So like spatial attentions, vision transformers. So this is still an old neural network from maybe 2000 or so. Okay, here that's what the training process looks like. You start off with saying everything's a majority class, everything's gray, gray is the street, because that's what a car data set mostly sees, the majority is street. And then you state over the epochs and learn your semantic content of the image, and then somewhat through the training process, always evaluated the same image. I mean, maybe somebody recognizes Bochum, but that's also from the cityscapes data set. And then you see that little by little, the scene stabilizes and the semantic content emerges. That's us. These are the humans. Yeah, and in the first iterations, we were literally not present, so completely ignored. And also now we're more unstable than the majority classes, like here street and so on. So the problem is we're small, we don't have many pixels. Yeah, so therefore, finding humans in street scenes is like finding an extreme minority class. And you all know that that's not so easy. Nevertheless, as more and more data is evaluated more and more times, so also here the stabilization takes place. There are other things here, like the info signs, that are still also a little unstable. And this is only one image. So there might be other instabilities on other images. So there is no guarantee that this works to 100%. Yeah, and let's do the following thought experiment, which hopefully will never come true. They are probabilistic machines, so they put off probabilities. Yeah, so obviously there was something that should not happen, but was it a defect? Did the neural network not work? That's a good question, because it might have turned out the right probabilities. In one of somehow 1 million cases, there is a person. Yeah, so the probabilistic nature of the machine learning algorithms, that poses a lot of new questions in terms of functional safety. And because you could go to the, you would say, if this happens, the thing has to be repaired. Yeah, but the AI engineer might say, this is just as predicted. Yeah, it exactly says the right probabilities. Yeah, so these are new questions, new sets of questions, where we have to start thinking about, also with the contributions of science. Okay, so if a person is overlooked, or if anything else is overlooked, or an error is made, then there was an event that maybe is rare, but happens. These things come with the probabilistic nature of the output, because these tensors that were output from the from this here. Yeah? So this is only the tensor after taking the argmax, so taking a decision, right, on which class to pick. But truly, there's an entire distribution on all the classes, on all the 90 classes behind every pixel, right? You could take cost-based decision rules, which I believe you should also do, yeah, and not take the argmax. However, yeah. Now, if we have a probability tensor, obviously, in probabilities, there's something like a mean or a standard deviation, right? So if you have a class distribution, yeah, you would say there is nothing like a mean, because taking the mean between cat and dog doesn't make sense. Yeah, but there's what we call the mode, so the highest probability, the thing you would turn out by the argmax, and there's dispersion. Yeah, so and there are various ways to measure dispersion. Yeah, like the good old entropy here normalized to 0, 1. Yeah, you have somehow the margin. This here is some 1 minus the probability that you have the right class. So it's simply essentially the prediction of the neural network, the probability of the highest class here. Somehow we did everything that 0 is lowest value. Yeah, 0 uncertainty is the lowest value and 1 is the highest. That's why there are some funny calculations. This is a Gini index, yeah, like usually used in social sciences, and it's somehow you look at the classes as if they were persons with a certain capital, and then you put persons with a capital in a row, and then you compare that with a line where every person had the same capital, and that would just go up on the diagonal. Yeah, and some of the free area that is below that, that gives you the Gini index, right? Yeah, so and somehow here are some classes which are rich, yeah, which have a lot of probability capital, yeah, and others are poor, and therefore we can build a Gini. So here we have 3 classes, but as the third class is a function, the probability of the third class is a function of the other 2. I only need a 2D representation to depict that. Yeah. And then you can, and this here is a difference to the next leading class, for instance. Yeah, so these are all, so we have the best class and the second best class, and how big was the difference between both of them. That's somehow also, if you think that the neural network has to switch from one class, if there's an edge, to the other class, and there has to be there's a certain stiffness of the neural network. It can't just switch like a sharp edge. So there necessarily you would somehow go through a 1 on this metric. Yeah. And then, of course, you can just do a heat map by applying these metrics of dispersion on the image, yeah? And then heat map the dispersion over the image. You could also heat map other ways of uncertainty quantification, like Monte Carlo dropout or whatever you would like, yeah? And then look at the standard deviations. And then obviously you would also get a heat map. Now, the question now is, what do you do with the heat map? I mean, it itself gives a good information. Like, I don't know whether you can really see this very well, but here on the left-hand side, there's strong networks. That's exception. Here is mobile net, so like an edge device for quick rendering of scenes. Yeah, so this is a little slower. So presumably that's what you would rather find in a car, but you see quality is worse. Yeah, and here are some misclassification. This is classified as building at this spot, but it isn't. There's street, right? But fortunately, these misclassifications all come with bursts of entropy, which is depicted here. Yeah, so on every pixel there sits a vector of probabilities. You compute the entropy and give that to the red scale. Yeah. So we have some chances to really detect these bad spots, yeah, and do something like an online assessment of the quality of your predictions. Yeah, you first give the predictions through the networks the best you can, but thereafter there's a second level of reflection whether this is somehow is a safe prediction or not so safe. Yeah. Okay, and here you see also something which I would like to outline. If the car companies go for automated driving, there's a saying there's always, with almost everything, you can make things a little cheaper and a little worse. Yeah. So the hardware invest is going to be a major political issue, I believe. Yeah, somehow to urge the car companies to invest in. I mean, obviously they don't want to make NVIDIA happy. Yeah, because then a lot of the money they will earn for the cars will go to chip companies. But if you take two bad networks, because you can run them on edge devices, you really lose quality. Yeah, and nothing like that is mentioned in all on legislation on automated driving, which is quite interesting. Okay, now it's getting stuck again. Okay. Yeah. Okay. Okay. So in 2019 we worked, or in 2019 we finished working on something we called meta segmentation or meta classification. Yeah. So the question now is the prediction I'm giving, is it correct or not? Yeah. And of course, you could do that pixel-wise as well, but that's not so interesting because I don't really care what a single pixel does. So what's much more interesting here is to do it segment-wise. So in the absence of instance segmentation, you can still collect connected components of the class masks that are turned out by the segmentation network. Go for the connected components and then average these uncertainty measures over these components. Add geometrical features, like you observe that if it's a misclassification, often the shapes are wiggly. Yeah. And so you average dispersion measures, you add somehow measures for fractality or somehow relationship between surface and volume, yeah, or diameter and surface, better to say, and position. Yeah, somehow things on the edges are less well detected often as things in the center of the image, and then collect these as handcrafted features and then predict the quality of the image by a simple machine learning algorithm, like in this case, logistic regression, or we've also been pretty successful in doing that with gradient boosters and so on. Yeah. But here, so you take somehow your standard logistic regression, there's nothing special in it, and you then train this here on all the connected components that are turned out by your segmentation network. And then you train, is it a correct or incorrect thing? And now there's something like interception over union, which is simply prediction. So this here, my arm isn't working so properly, so that looks a little funny. So if I look this here as a ground truth, and this is a prediction. So I have this part here, which is not a good prediction, and that part is missed. So that prediction is also not good. So if I then take this here and divide it by the entire shape, then this is a u. That's a number between 0 and 1, obviously. And you could also do not only meta classification, is a segment I predicted, is it really there? So that's question number 1. And question number 2 is, which IOU does the segment have? So IOU 0 would be, there is no pixel in the ground truth that actually corresponds to the prediction you're making. Yeah, like here, right? There's no building. There's only street. So that's an IOU 0 event. And other things like that here, the IOU is that, but we've missed this part. So the IOU of this year is maybe 80% or so, yeah, of that prediction. And then you can train not a classification, but a regression model in order to predict the quality of your perceived segments. Yeah, and that's now an example what you get out. So here's the humanly annotated ground truths from cityscapes again, cityscapes data sets. So you see a lot of manual labor going in. This here is the prediction by a rather strong neural network, or at that time rather strong. So it's this section 65 with backbone, with a deep learning decoder. So the backbone exception 65 and the decoder is deep. So here you see now, yeah, and that has IOU 0. So comparison with this and this gives a red flag for the IOU. Yeah? So this is something you would like to have as a quality assessment of the predictions of your neural network, like a self-monitoring. But obviously, you don't have this information in deployment. Now, when you deploy your algorithm, you simply don't have somebody annotating it for you. So what you then do is someone estimate this by the procedure I just outlined, yeah, by meta regression. Somehow the similarity of this image and that image, that's then the goal. Yeah, and here you see that this here has been predicted, but to our algorithm, it's pretty clear that this is not the prediction. So it rates it with IOU almost 0. For the street, I mean, there, of course, you always get a good prediction because street is very large and you have to be a little careful. Look at this here, for example. Here's a little mistake. A broadwalk is predicted. Port. Yeah. So that works pretty well. And here's another image. Yeah. So pretty accurate predictions. And here's a mistake. Yeah. So this is predicted as a part of the street, but it's completely broadwalk. Yeah. This is therefore all red and pretty. Yeah. So that's somehow the success of the method. Like always in machine learning, nothing works to 100% accuracy. So that's not a solution to all the problems, but it might be a small contribution. Okay, here's some regression plot of and the IOU. Yeah, and there's something interesting here. Yeah, so these are IOU things that actually have 0 IOU. So somehow quality is very bad, but predicted very well. And my former collaborator, now independent researcher, Matthias Rodman, he had a closer look in this, and he detected quite a few labeling errors. So this was a very good way of detecting quality problems in data sets. And I think that's a very interesting direction of research. Now you go over to videos. If you have segments, you can track the segments because truly you're in a dynamic scene. And well, then here you go. And we give IDs to every segment, and then we try to, well, somehow engineered rules we try to follow up with the segments, and then collect the uncertainty quantification along the somewhat 10 frames or something like that. That's work with Kira Mark. And by the way, Kira is now a postdoc in Berlin with me, but she's going to be junior professor in Düsseldorf from October 1st on. And yeah, you track instances, and then you track the uncertain information. So all the features you can arrange in a time series, and then make even better predictions in a time dynamic manner. The big problem is, if you want to evaluate that and train that, you would really need video annotations, yeah, which is obviously very expensive. So this is a kind of proof of concept with teacher-student network. Yeah, but obviously the errors that the teacher network makes are quite disturbing. But nowadays we have so strong networks that this could be worth a second look. Here you see the situation. I think that's a teacher network. It's a little unstable mobile net. That's the exception. And here somehow, whether this is parallel or not, whether here you see the same image, that's then the quality measure for our method. Well, you see, it's hard to judge. So let's do it in a little more controlled way and look for GTA 5 data. Yeah, because there you have every frame annotated and the Viper data set, therefore you can have a perfect round truth. Yeah. And now someone having these things here in parallel, that's again the quality measure. And you see that like these things that occur here, because I mean it's GTA 5, it's a dirty town, there's litter line everywhere on the street. And some of the litter detection works quite well in this case. So far we that's joint work with Aptiv. I think Aptiv is one of the best AI design R&D departments in North Rhine-Westphalia. They're situated in Wuppertal, so our collaboration when I was at Wuppertal was quite natural. This is LiDAR data, yeah, so and presented from a bird's view. As you have this point cloud, you get from sending out the LiDAR rays and waiting when they come back. The colors you see here are again segmentation of the points. So that you have some of these pointers, and for any ray you've been sending out, you try to find the class. So there are different ways how to do it. You could either somehow do a stereographic projection on like a screen, yeah, and then somehow for wherever the ray hits the screen, you can do your classification, or you can do an interpolation there of colors and then use standard 2D segmentation technology, or you could go for something more elaborate and really work on 3D point clouds. Now here's the same game. We have here the prediction of the network. Here we have the ground truths humanly annotated. And here we have direct comparison of the prediction and the ground truth. So there's an arrow here. Yeah, this here is our meta regression tool, which somewhat, well, I mean, maybe it's not perfect, but there's some indication that not everything is perfectly okay here. Yeah, so we can somehow also interpret this LiDAR data by essentially very similar things. Okay, these were errors that could have been avoided by a better network. But there are also forced errors. There are errors which are unavoidable if the neural network has been trained in a closed universe. Yeah, and these unavoidable errors come up if you confront the neural network with data that is simply not represented in the semantic universe on which you have trained your supervised model. And like the cityscapes classes, there's been a choice of picking these 19 classes, yeah, and sheep haven't been chosen. Yeah, and that's why there's going to be a funny class salad if I put this image in a segmentation network. Yeah, and what you see here is this green lines. Yeah. And the green lines is now the annotation where on the image is something which is out of distribution semantically. Yeah, you have many ways of being out of distribution. You could be out of distribution in terms of light circumstances and so on, but you can also be it in a semantic way. Now, there's a Corona story behind the green lines. During Corona, no company accepted students anymore. Yeah. So at University of Wuppertal, and we had mandatory internships. Yeah. So there was an exception of doing internships in university at that time. And that helped us to label quite a few of these out of distribution data. Well, we also gave Python courses, and so I think it was a fair deal. So this was not like, oh, you're there. I have click work and click work and click work for you. I think it was a fair split. Yeah. So we had like teaching elements of one half, and the other half was click work, and we created this out of distribution data sets, which then joined with similar efforts from ETH Zurich and EPFL, which somehow converged into the segment me if you can benchmark with Robin Chan, who's now also at TU Berlin as a main author, one of the main. Okay. And then the question is, what happens if the sheep actually occurs on the street? So here's a sheep on the street. That's a standard network. So just trained on cityscapes. Nothing else. You see, there's a red lag. Red means human. Having a lag, maybe that reminds humans. There's something green. Sheep has grass in his mouth, but yeah. And there's street, which is not particularly good for the sheep. So I think the red lag is what presumably would have saved this sheep. Actually, it's just copied in there, right? So no animal was damaged in this set of computer experiments. Now, this is the dispersion measure, entropy, which I just introduced to you. And you see there's a little bit of highlighting the sheep, yeah, which corresponds also to this diverse classes. So there's not too much security, but I mean, this color, that color, and you will not see the star that's in a related scale. Yeah. So you obviously need some filtering in order to distinguish between that entropy that makes you nervous and things that just happens as false positive. Yeah, false positive alarms. And that would presumably not have been good for the sheep. Yeah. So what to do to save the sheep? We proposed that trained on pizza, on chairs, on all kinds of stuff, on cocoa classes, but none of the classes were neither the classes that we had in the out of distribution data set, nor which were the cityscapes. Yeah, and we trained the network to respond with high entropy to any of these cloud of out of distribution classes. Yeah? And therefore somehow made a kind of natural reaction to be to respond with high entropy if you see something that you haven't seen. And then you see that somehow training on all kinds of stuff, but not on sheep, make this here pretty red. Yeah, so somehow was an out of distribution object. We had this published at ICCV in 21, and at that time we've been somehow #1 in the benchmarks, but obviously in computer vision, this doesn't last long. And in the meantime, there are quite better methods available, mostly transformer based. Yeah, so it's like Andy Warhol said, anybody can be famous for 20 minutes. That's quite, quite close to what we have in computer vision. Okay, here's some numbers. As I said, by now, outdated, so I just switch further on. Now, my working group has a funny title, Mathematical Modeling of Industrial Life Cycles. And as I do a lot of machine learning, as you see, or computer vision, natural question is, what does it mean for, what does a life cycle for an AI algorithm mean? Yeah, so at the time, we're so busy of bringing the thing into the field that we're not really reflecting what's going to come afterwards. Yeah? So there is natural questions coming up like customizing AI, yeah, because not one size fits all for AI might not be good. I mean, we have seen these out of distribution categories. Usually you don't have to recognize a boat on the street. But now somebody lives next to a sports harbor where some of that's quite frequent phenomenon. Yeah, that boats are towed in and towed out of the water. And they're on, here you see the Brandenburg gate. And we said, okay, now humans are out of distributions. We erased the human labels from cityscapes, right? Just for thought experiments. And now you see here, okay, humans were rather recognized as cars or some or building or whatsoever. Yeah. So here you see the uncertainty masks, and that says, okay, we have not recognized the humans because we were lacking the word human. Yeah, but we can have pretty clear indication that something strange is going on here. So we can retrieve all these strange instances and then pseudo-label that. In this case, here we have here some new orange pseudo-labels. We do only that in the case where we're pretty sure. And then retrain with a pseudo-label of this new class that doesn't have the name human, but somehow XC5P3. Yeah. But nevertheless, it's somehow a new class, and it is somehow then giving a certain degree of recognition. Yeah. So that is unsupervised continual learning for semantic segmentation. That's a pipeline. As I already said, is we start off with our input image. Then there's an initial segmentation. We see these are the highly uncertain spots. We click that. We send that through an image embedder, yeah, like at that time DenseNet. And then we had features to be extracted and try to cluster that and constitute from the denses cluster new categories, new artificial categories, and then pseudo label them, train them. And if you do this kind of continual learning, so you have a baseline network that was somehow segmenting in a world without humans or in a world without dogs, yeah, and then you learn human or you learn dog, and then you will have the catastrophic forgetting of the old categories. You have to do something to countermeasure that, right? So either you go for replace strategies that you somehow bring in old classes, or in this case, as we have always mixed images where there is humans on the image or dogs on the image, but not exclusively. Yeah, we have for those things that are somehow well predicted, we have somehow this of the Kullback-Leibler divergence between of just on the set of all the known classes, right? And we force the new network to give the same Kullback, so to minimize Kullback-Leibler distance between the probability vectors that are there. Yeah, this kind of loss function then stabilizes the network and guarantees that the performance on the old classes is not ruined. Yeah. And now here you see some results. So that was original prediction. Human class was unknown. Here you see humans somehow nicely detected. Yeah, then you have prediction after the pseudo labeling, and this here is the ground truth. Yeah, so somehow without ever providing any label, in this case, somehow 40% IUU of humans in cityscapes have been achieved. Now, that is okay, but it's not everything, because there could be classes that are quite close to other classes like car and bus. That's also just a matter of discussion on the taxonomy you're using as a bus a car, yeah, or a both vehicle. Yeah, and that's a good question. So if you have a near category, which is not well separated, human is quite outstanding in cityscape. So there's no other category, maybe rider or so, but this is very, this is a very small number of pixels. But this here is, of course, predicted as car, but also with high uncertainty. Yeah. So this here can be retrieved, and then this is the ground truth, and this would be the thing after pseudo labeling. And this would be the area that is somehow drawn out from this segment. Yeah, so it's the same segment, which is blue here, but somehow the uncertainty leads to the construction of a new bus class. Yeah. Okay, that's some of the next level of difficulty. Works to a certain degree. Yeah, like we have here also around 40 for the bus class, which is okay, but not brilliant. Yeah, and yeah, cars, if we erase cars, that's really easy because we have a lot of data and so on. Yeah, that's easy to get. We have something like 81% mean IUU, which is really, really good through this procedure. And here you see humans, cars are really well. So these are humans that should be recognized. And these are humans detected after the labeling. And here we have pseudo labeling and the trade. Here we have cars. And here we have humans and cars. So think of, we don't learn one further category, but a number of them. Yeah. Okay, I have to click on here once more. Okay, now the last experiment in that direction is going for that with a change of the environment. So training on cityscapes, but then drive out in the countryside. So add a domain shift on top. Yeah, and in the countryside, there is something which is guardrail. Yeah, you hardly ever see that in the city. Yeah, there's a lot of guardrails, and the A20K data set that is essentially countryside, and cityscapes is essentially inner city. Yeah. And therefore, you can somehow constitute new classes here. And it's a ground truth again. And I mean, this is a good image, obviously, but guardrail has been nicely recognized, but only to 20%. I mean, IUU, which is okay-ish, not brilliant again. So I think this kind of thing is underway and only at the beginning, and there's certainly a lot of room for improvement. Okay, now I'm switching again to the thing that are going to happen in the future if we have success with deploying our artificial intelligence model. So think of the life cycle again. Yeah. So there is this time an accident involving a deer, right? And we're not happy with what the car did in the case of the deer. And therefore, there is a team formed, say, in some automotive company, which should fix the deer problem. Yeah. So what's the first thing the team is going to cry for? Data. Yeah. I want deer data. Yeah. Give me tons of deer data for testing. Yeah. But nobody knew in advance that it would be a deer that created the problem. Could have been something else. Yeah. Who knows? Yeah. So the strategy to work with that is to use vision language models upfront, obviously, yeah, to employ contrastive learning, and have good embeddings, semantically meaningful embeddings trained on billions of images, and then use that for somehow ex post labeling. Yeah, so we retrieve our OOD objects, we let them go through the image encoder and save the encoding of the of this OOD object. Yeah, and we collect OOD objects regardlessly what they are. We don't even label them. If it happens that somebody cries for deer data, so that's now the head of the group crying for deer data, by the similarity of feature and image embeddings, you can retrieve the deer data. And of course, like always, not with perfect quality, but that's essentially then the set. Yeah, and we did this on video data because on video data you can detect the things very well if they're close, but then you can trace them back in further distant locations where they might be even more relevant because you, I mean, if you have the deer right in front of you, it might be too late. Yeah. So, and well, that's here essentially a combination with OOD detection. I've been talking about this. Somehow we cut off boundary things that somehow on the sides of the street, there are often many things that are not interesting for us. So we focus on a region of interest, which is the street, then we track. Here things are small, bigger. This was small and now it's getting bigger. And somehow by tracking with a high sensitivity, if we're then very sure that here we detected an OOD object, we can trace back that and have some of the information on more remote things. And then obviously, according to this time series of images, we get a time series of image embeddings for the clips we extracted. That was, we have a text prompt that was similarity. Yeah, we can somehow with the angle, and those which have a small angle with respect to to the prompt we've given, and then collect. And maybe review by humans whether it's really a deer or maybe something else, and then retrieve. Okay, and here are some examples from Supergiant Street Chaos dataset. We had a lot of fun creating that, and you see, you can somehow find the balls and find stuff. Okay, now vision language models. I'm a little rushing because I feel my time is off. That's for me a new kind of encoding. And if you look at the features that are generated by a vision language model, they're already semantically quite distinct. So somehow there's a really good way of extracting excellent features from it. And if you look at this here, for instance, for a scene like this, you see this is an image net supervised training, pre-trained neural network. These are the features of that. The features are built in a way that we made a TSME embedding in 3 dimensions and coded the values as colors. You see here, you see some features well extracted, and that's meaningful. But if you look at the ELA clip embeddings, this quality is much better. You see the semantic separations. And that's, of course, behind this kind of brilliant features. That's what's behind this fascinating zero-shot segmentation performances that we have nowadays. Okay, but let's simply take this here as an encoder, throw away the old ImageNet encoders, chop the clip off like a Sunday egg, and put a decoder on top, fine-tune everything a little bit. And then all of a sudden you get something like that. On the Cityscapes benchmark, this is a leaderboard. We have our 20 minutes, which just started a few days ago, and present way we are leading this benchmark without actually having a true contribution, just by combining powerful features with a powerful decoder. But there's something more behind that, and that is we have a second domain, and this second domain is multimodal and it behaves differently, like if we humans describe a scene, we have a bias. We don't describe every detail of the scene, but we describe the action, and the action is mostly domain independent. So if I see 5 people at dawn, I would say I see 5 people on the thing and do this as a description. Or if I see a car at night, I would say I've seen a car. And in this way, with high probability, the text description that you associate with an image will be similar or the same, regardless what the lighting or so was. These are somehow circumstantial facts that, of course, you see, but you leave away in your language domain, because the language domain, you're abstract from it. And in this way, with high probability, you have the vision domain 1, say daytime. You have the vision domain 2, say night. You have a translation between the vision domains by just changing the lighting. I think that's something you can do with computer graphics methods, or if you wish, you can train a cycle gun or whatever. And then you have the same textual description. And then you have the clip training, which somehow aligns the feature embeddings from the vision encoder and the language encoding mode. So they're forced to be the same. And that in particular says this here has to be like that because it sticks around the same text code. So you tie these feature embeddings together to the fact that the language domain is largely invariant under the domain should we consider. Now, these are contrastive learning. And then you stack anything like a vision decoder, segmentation network, object detection, whatever you wish. Stack anything. If that's already the same here, it can't change. That's a function, same argument, same value. Yeah. So in this way, you get somehow a high degree. I mean, this is idealized because that's only valid if this alignment is precise without any difference, but it works in practice. Yeah. And that's somehow this was a Cityscapes benchmark that was only an accident. What we really wanted is to look for Cityscapes trained network or networks trained on a virtual world like GTA 5 or like Cynthia, and then evaluate on Cityscapes, or look at Cityscapes trained data and evaluate that AC/DC, which contains snowy data, bad weather data, night data, all from Zurich. Yeah. And as you see, this table was what we were really. So we somehow changed the bench about 15% at that time, just by the simple trick of multimodality. And we also, for the first time, that the domain generalization method was somehow of the same strength and the unsupervised domain adaptation method. In unsupervised domain adaptation, you have the images from the other domain, however, not the labels. Yeah. Okay. These are some of the results. And here you see a network that has never seen snow and performed on snow. This has only been trained on daytime and you evaluate it at night. Okay. I should say that we've been the first group to do this, but only by a margin. And there were two other papers that went into a similar direction. Okay, so this is an outline of the talk. As my 60 minutes are over, maybe a little more. Just say thank you very much for your attention.
For the questions, we stop the recording, and he is more flexible to answer freely, and the people in the audience can ask more questions. So, who wants to ask the first question? Maybe you from the audience. Yeah, thanks for the talk. I would like to come back to the retrieval of ordered distribution objects where you have used the pseudo labeling. I was wondering, is there any guarantee about the performance improvement with super labels? Or is there any additional information that you get into the pseudo labels from different kinds of models, something like that? Because if you just use a model to predict the data and then use the same predicted data for training the same model, then there would be no information gained, right?
Good question. I can only give a very vague answer to that. There was a best paper award on NeurIPS, which was on statistical learning guarantees for out of distribution detection for classification. Yeah. That could be a hint in the direction that actually beyond empirical observations, you could do something in a guaranteed and mathematical, well-founded way in that direction. But obviously, like always, these things, they give you guarantees in some limits, but not really for the amount of data you're dealing with in the real world. So I would say this is mostly empirical. You have observation. You can always go for better testing, a more extensive testing. That's presumably the way to go to get empirical guarantees by piling up experience.
Okay. But it's Are there multiple models involved? Because you do have this uncertainty quantification as well. Do they at least?
Of course, yeah. So you really have a pipeline, and that's also what's getting somehow scientifically a little odd, because there are so many parts of the pipeline you could exchange, and they has a tendency to interact with each other and so on. So I would say all this is in a preliminary state. Yeah, we try to be early in pointing out that there exists a problem, but I think we're far from a final solution. Or we could not say that this is now solved by no means.
But with this, at least there's some enrichment of the information compared to only using one.
I would say some of the things I've been showing will probably somehow get much more advanced by this open vocabulary segmentation stuff. So I think from that on, we will make progress in that direction.
Yeah. Great, thanks.
Yeah. Okay, cool, thanks. Yeah, yeah, very interesting. I work in philosophy, so I'm sure I missed out on some of the technical stuff, but it sounded really cool anyway, and I saw lots of connections. And then one that I'm interested in is you said that you have a way of representing how confident the system is on its classifications, right? So you can tell how uncertain it really is. And I mean, this is like
tries to,
or it tries. Yeah. In philosophy, you would maybe it's very similar to suspension of judgment, where you're going to realize you don't have good evidence, so you don't form a belief. And then one thing that's interesting in philosophy is how that ties in with how you act on that basis, right? And then I don't know. I mean, it's not there. I think there's lots of discussion going on, but one typical way to respond to suspension of judgment on something is that you don't act on it, or you're like treated with more caution. So the interesting thing to me is like, how does that connect? How does it translate into how, say, your automated vehicle will then act if it's uncertain?
This is a really good question. I would hope that there is a little downstream program that says, if I see something like that, I drive defensively, or I return to a safe state, So, or I call the big brother in the cloud, and really shoot with the best recognition. I can't solve this on the edge, so let's ask a really strong model in the cloud. So like options like this are on the table. What's the right thing to do will evolve.
So, but your group focuses on the vision part, and then like it's somebody else who will have to
right
deal
afterwards. There comes the downstream things like what do you do with a perception?
Exactly.
And then you now think you perceived something, or you made a environmental model, and then comes a planning task. So you go from the perception to an environmental model, like a bird's view, where the other agent's sitting, and then you take your decisions. How are you going to do your decisions? This is somehow, some people do it end to end. They take the mask and then train a reinforcement learning network on it. Others engineer decision making. We're now in a new consortium that is going for generative decision making, so generate decisions. Get into an image, or you could try to go for imitation learning. We are now in a field where we have too many options, so we don't really know what to do, and we have to find that out.
Maybe just following on to what I think must have been the question. I just had to go out and come back. Do you see a kind of an avenue for bringing in sort of old-fashioned rule-based layers here on top of the whole thing? I mean, as a logician, I sort of ask myself, okay, so we have these stochastic machines, but don't I then need, on top of the whole thing, some sort of rule system that says, if this system thinks it sees this or that with certain probability, I'm going to kick in a fail-safe, fail-over like return to base point kind of algorithm. And that's going to be some deterministic stuff. It's not going to be stochastic. Is anybody thinking in that direction? I'm aware that there's a cultural problem here because you guys don't like logic. You like numbers, right? So,
No. I think I'm not speaking for myself, but for the general attitude that I see in the community. I would say that people, I mean, there's been 20 years of computer vision prior to deep learning. Yeah. And already the weakest deep learning frameworks, which were based on the convolutional architecture, outperformed these things. I mean, you know, the first automated driving trip from Munich to Nuremberg, that was in the 80s. I mean, they didn't have neural networks in there. They had classical computer vision, but I would have been really nervous sitting in that van, right? I think the neural networks have a fascinating performance, but what we also realize is the accidents that actually happen at weird points where we would never have anticipated that. Yeah, and that's we're now confronted with something that has fascinating performance, but sometimes does really weird things, and not at the points where we would expect. Yeah, so it's like overlooking something which is simply too big, like the accidents of the car running below the truck. I mean, if you know the architecture of neural networks, you say, okay, convolutional neural network, the thing has simply been bigger than the perceptive field. Well, yeah, but that's something you would not come to the conclusion as a person which would somehow try to find rules. Yeah, so therefore, I think it's always tried to do, but it's rather done now at the interpretation of the data. So like an ultimate logical layer after the perception task has been done. I have proposed a machine learning approach to quality things, but you could also try to bring in logic there. Yeah.
Maybe only to find a compromise between you two, like what Lamar Institute is also about is this hybrid machine learning methods. That's one part of our triangle. And maybe that's also like for Eva being also more trustworthy concept at the end where you can convince decision makers, either being the driver in the car or like someone doing the real decision of the factory, whatever. So I think it should be both, right?
Yeah, but as I said, I think it makes a lot of sense to do this kind of interdisciplinary research. I mean, there's been a colleague from Munich who tried to find the envelope of all actions of other agents that were according to the Straßenverkehrsordnung. Yeah, and to be robust against any possible action of the other agents that does not violate the law. Yeah, like then there's an interaction between law and planning. Yeah.
My question was more on your deer. Like I feel this engineer that needs more data from the deer to train the algorithm, but it's only one example where you had an accident. I was thinking about your unsupervised method that you presented at the very end. Wouldn't you need something to predict you the empty white spots of your data space where you simply don't have data before doing an accident?
That's what really something we have in mind. So that's what you call the long tail, right? So you have the 19 classes, but these are only the majority classes. And then comes a long tail of everything you pushed away. Yeah, and the long tail, you can now fantasize a lot how the long tail would look like and how that depends on countries and so on. But I think one proper way of dealing with a long tail is retrieval. And that's something we have in mind, because I think a retrieved long tail, which comes from reality, that could be quite valuable, because then you can also speak of frequencies and stuff. How often happens this and that.
Yeah, thanks first of all for your talk. I really enjoyed especially the images that you showed, a lot of animals. And I have a question regarding video prediction. So in the examples that you showed, we saw that during the course of the video, there are a lot of inconsistencies. For example, we drive across the street and we segmented a building and then we drive over the building. Or there's a building and the next second is classified as a deer, for example, which of course for us in a world that is constrained by some physical rules is very clear that this is a wrong prediction. Is there also a way for the model to kind of learn from this? So for example, if we drive over a building to go back and see, of course, this prediction from a couple time steps ago is wrong.
This particular thought is new to me, but if you combine, I mean, usually you do the perception frame-based, and you add the logic that something can't just vanish in the tracking. So if there's an occlusion or something, you would say, okay, if there is something re-emerging which is similar enough, or so I give it the same identity and I track this on. Or if I just missed, that's also one of Kira Mark's work with reducing false positive by which are just this flickering that instances have been missed on single frames, and using that for false negative detection. So what we have been doing was mostly false positive. She's also doing false negative. So yes, this temporal consistency is an interesting research direction. And I personally believe that the new technologies coming from video generation and this dynamical tokenization, the people really achieved it to make videos temporally consistent. So I see a lot of potential in looking into what they found out and try to engineer that for my problems.
And do you also have some form of physical consistency? So for example, a house in the sky is quite improbable, except if we have some tornado also. So can you also integrate physics-based rules into your models?
I didn't do that ever. Despite being a trained physicist, but I think it makes sense, to enhance this thing with this kind of logical checks. But I would see that as a part of a downstream task. And of course, somehow the logic is also a little bit dangerous. I mean, it's not only bringing safety, but if you excluded a case which funnily somehow still can emerge, you force the system to miss it. So interesting set of problems, but that's job security. As long as we didn't solve the problems, they cannot fire us, right?
At the beginning of your talk, you motivated the talk using functional safety. But I was hoping that you could comment on how to actually utilize uncertainty quantification and robustness in your experiments linked to functional safety, which is very important nowadays for automatic cars. And what Jakob says, so currently they are used to rule-based, doing a lot of tests, but their robustness requirement is very high, right? So 10 to the power minus 6, 10 to the power minus 9 in terms of errors. You are actually looking at the segmentation errors and mistakes. They are probably not even important for functional safety at all, right? So
depends which of them.
So attention is what you needed for the functional safety as well. So how do we actually link these two together towards functional safety? How do you think?
part of this work has been done under this consortium AI Safety by the Federal Ministry of Economic Affairs and Climate Action. And that the results from this consortium also went into the ISO PAS 88000, which is properly on functional safety for automated car. Now, given that everything is quite emerging and quite unsettled, what kind of level could there be in such an international norm? I would say that there should be written something like, if you want to operate a fully automated system, you have to have an a state-of-the-art uncertainty quantification algorithm running. Yeah, and then we have some ideas what that could be. I mean, that could also then be a matter of the competition, but something like that I could imagine.
Last chance for questions. Maybe we give the audience from the web a chance, only if there's nothing in the chat.
There's no question in the chat, also no question on YouTube. Okay. We have another one. Can you go 2 slides or a couple of slides back to 37? That's the domain translation, and I was wondering, is it more of a theoretical requirement that there exists some translation between them, or do we actually need to have the function that does the translation? I could imagine that
it's a theoretical requirement.
Yeah.
And of course, I mean, if you have this is true, if you want to see this as a mathematician, it's a commutative diagram from algebra, right? So it's that if you compute it this way, you get the same as that way. Yeah, so somehow the passes you go to this thing always give you the same result. Yeah, and but you have to define the pairs that should be aligned. Yeah, and for somehow defining the pairs here, that would somehow I need this function. But function maybe is even too narrow. You could also imagine set-wise mappings here. Yeah, somehow as long somehow as a language description is somehow the same or similar, then this would still work. Yeah. So it has something to do with aligning the invariant manifolds, where you get the same semantic for the vision model. Yeah, aligning that with somehow that the domain translation acts inside this invariant manifold, and you do that by using an auxiliary domain. So we have one master thesis going on where we say, hey, what are we doing with active sources? You've seen the LiDAR stuff. Yeah? LiDAR does not care about external lighting at all. It sees at day the same image as it sees at night. So it's not even approximate domain invariant, but it's precisely domain invariant by physical reasons because of supervision of electromagnetic waves. Yeah? So in this way, if we somehow train an image LiDAR clip, we hope to be to have a kind of alignment as well.
Could you go even more? Could you have an even more of a kind of fuzzy alignment that's even looser than sets, just by assuming that there is in the language domain a similar description for 2 similar images, maybe with another log?
Well, if I'm not precise here, I'm running a little bit into problems here. So I suppose that in reality, this is not precise. It's only approximate, right? And the miracle that happens is that somehow the interpretation through the decoder network was still interpreting it in a similar way. Yeah, but if you see the brittleness of something like a decoder network towards adversarial attack, you know that very nearby there are other feature encodings that would probably spoil this nice result. So if you do this here too loose, you can lose on the top part of it.
Thanks. Very last question, JJ.
If I may, so does this only work for a text together with image? Can I, for example, extend this to multi-model fusion?
Now, this is mathematics, it's abstract.
Yeah, okay.
Yeah. So it's as I just said, we are now doing it for LiDAR image. Yeah. And the crucial thing is you need a domain invariance for the auxiliary domain, because afterwards you throw this away. You don't have this, you don't have a text encoder in the car. You just go this and this. Yeah, but during the contrastive learning part and feature extraction, you did this. Yeah, so yes, that's the beautiful thing about mathematics and abstraction. Whenever you have one domain invariance, then you can always try to apply this.
And it's also not limited to 2, right?
It's not limited to 2.
So then let's thank Hanno Gottschalk again. Really great talk. Maybe as he's here the entire day with us, so we still have some open spots, like after lunch, I think you have some PhD students meeting with him. So maybe if you got interested now after the talk, approach Jens Buus, and then you get another time slot between lunch and I think 3 o'clock is the next appointment that we have.
And thanks again for having me here and all the nice questions and the very good discussion. Thank you.